Good afternoon. My name is Jessica Drosty, and I have the privilege of serving as the president of the IMSA Student Council. On behalf of the entire Illinois Mathematics and Science Academy community, especially my fellow classmates, I would like to welcome our guests to our campus and to the 4th Annual James R. Thompson Leadership Lecture. I would also like to welcome Academy students, faculty, and staff to this special event. The Academy's foundation, the IMSA Fund for Advancement of Education, is happy to provide this opportunity for students from schools in Aurora, Chicago, and all over the state. I hope you will leave with a sense of the pride we have in our community. We have been looking forward to this day for some time now, and I know you'll enjoy the lecture. At this time, I would like to introduce the Executive Director of the Academy, Dr. Stephanie Marshall.
Thank you, Jessica, and good afternoon to all of you. On behalf of our Board of Trustees, the faculty, staff, and students at the Illinois Mathematics and Science Academy, welcome to the Academy and the 4th Annual James R. Thompson Leadership Lecture. I want to echo Jessica's welcome and say what a sincere pleasure it is for us to have all of you here this afternoon. We welcome you as IMSA partners and friends. Without your continued support of this institution, events like this would simply not be possible. Unfortunately, Governor James Thompson, the man in whose honor this lecture was established, was not able to be with us this afternoon. However, he told me he was a big fan of Dr. Ride and asked me to tell you that he would be here in spirit. And so, in the spirit of Jim Thompson, I also welcome you. At this time, I'd like to recognize two special friends of the Academy who are here today. We are delighted to have State Representative Mary Lou Collishaw and Suzanne Deutschler with us. They have been strong supporters of the Academy from the very beginning, and we are very grateful that they could be with us today. We are also pleased to welcome teachers and students from more than 60 Illinois schools, as well as members of the IMSA Fund Board of Directors, the Board of Trustees, and local government officials, including the Mayor of Aurora, Mr. David Pierce. And finally, we are delighted to welcome our corporate foundation and individual donors to the IMSA Fund for Advancement of Education. We continue to thank you for your generous support. In a very short period of time, the Thompson Lecture has become a treasured tradition for the Academy. Each year, this lecture enables us to invite distinguished leaders in science and arts to our campus. We were fortunate to have Dr. Carl Sagan at our inaugural lecture 3 years ago. Dr. Edward Teller was our guest speaker 2 years ago, and Dr. Maya Angelou spoke with us last year. Dr. Sally Ride continues this extraordinary tradition. In light of the Academy's mission and our focus on integrative ways of knowing and connections among mathematics, science, the arts, and the humanities, we could think of no one more appropriate than Mr. Michael Burke to introduce our guest speaker today. Mr. Burke is the founder, president, and chief executive officer of Tell Labs in Lisle, a company whose voice and data equipment is used worldwide, and he serves as a member of the board of directors of the IMSA Fund for Advancement in Education. In addition to serving on the fund board, Mr. Burke has played an active role in supporting our students and our academic programs. And this past year, several IMSA students have participated in our mentorship program, conducting research at Tell Labs. Before founding this company, Mr. Burke was a member of the technical staff at AT&T Bell Labs. He managed the transmission system design department at Continental Telephone Labs and then served as Director of Engineering at Westcom. He has served as Chairman of the Telecommunications Association in 1991 and continues to serve as a member of its board. He received the Illinois High-Tech Entrepreneur Award from Pete Marwick and Mitchell and Crane Chicago Business in 1984. In 1991, he was named a Purdue University Distinguished Engineering Alumnus, and in 1992 was named an outstanding electrical engineering alumnus. Would you please join me in welcoming one of Chicago's premier entrepreneurs and business leaders, Mr. Michael Burke.
Thank you, ladies and gentlemen. With an introduction like that, I think I should be the one doing the speaking here. Fortunately, I'm not. Thank you, Stephanie. It is indeed a privilege and an honor for me to introduce the speaker to this 4th annual James R. Thompson Leadership Lecture. Among the numerous achievements, Dr. Sally Ride, former NASA Space Shuttle astronaut, is perhaps best known as the first American female astronaut to travel in space. Dr. Ride currently serves as physics professor at the University of California in San Diego. In addition, she is director of the California Space Institute at La Jolla, a research institute of the University of California. Dr. Ride began her preparation as a distinguished career in leadership, public service, education, and research while attending Stanford University, where she received no less than 4 degrees: a Bachelor of Science degree in physics, a Bachelor of Arts in English, a Master of Science in Physics, and a PhD in physics. Sally knows something about physics. In 1978, the year she received her doctorate, she was selected for astronaut training and reported to NASA in July of that year. Since then, she has been regarded as a pioneer for women in the U.S. space program, logging 337 hours as the first woman to travel in space. As part of her training, she was a member of the support crew for both the 2nd and 3rd shuttle flights and worked in mission control as the capsule communicator for both of those missions. Dr. Ride has flown in space twice. Her first flight was aboard the Space Shuttle Challenger in 1983, when a 5-member crew deployed communication satellites for the Canadian and Indonesian governments and conducted materials and pharmaceuticals research on the mission. This was the first satellite deployment and retrieval using the robot arm on the shuttle. Her second space flight was also aboard Challenger in 1984. During this 8-day mission, the crew deployed the Earth Radiation Budget Satellite, conducted scientific observations of the Earth, and demonstrated the potential for satellite refueling by astronauts. In 1985, Dr. Ride was assigned a 3rd space shuttle. Unfortunately, during the training for that flight, the training was interrupted by the unfortunate accident in January to the Space Shuttle Challenger that killed all 7 of the individuals aboard. Following that disaster, she served on the Presidential Commission investigating the accident and was assigned to NASA headquarters in Washington, D.C., defining long-range planning for the U.S. space program. During her work at NASA, she created the Office of Exploration and co-authored a report on the future of the U.S. space program. In 1987, Dr. Ride resigned from NASA to accept a fellowship at Stanford at the University Center for International Security and Arms Control. 2 years later, she moved to her current position as director of the California Space Institute. Dr. Ride has received the Jefferson Award for Public Service and has twice been awarded the National Spaceflight Medal. In addition, as those of you know who lined up to get her autograph in the auditorium, she has put her English degree to pretty good use, authoring a children's book entitled To Space and Back, and 2 other books entitled Voyager and Adventure to the Edge of the Solar System, and The Third Planet, Exploring the Earth from Space. Today, I am very honored to introduce a woman who has dedicated her life to researching and advancing scientific knowledge, exploring the beauty, wonder, and importance of space, and educating our students and the general public about its value. Please join me in welcoming Dr. Sally Ride.
Thank you very much. After an introduction like that, I feel that I should sit down immediately so as not to destroy the illusion. Actually, as we were walking in here to the gym, we were all remarking that this is the most dressed up that any of us have ever been in a gymnasium. I suspect that many of you feel that same way. What I'd like to do this afternoon is to try and give you some sense of what it's like to be in the space shuttle, what the experience itself is like, and also to try and tell you just a little bit about a program that's going to be a very important part of NASA's future over the next 10 years, maybe even 2 or 3 decades. It's becoming more and more important as we learn more and more. And that NASA program is Mission to Planet Earth, exploring the Earth from space. So you're probably very glad to know at this point that you're not going to hear a physics lecture. You're going to actually hear much more about the space program and my experiences in it than anything particularly scientific, although I know that you're all budding scientists and engineers out there. The way that I've chosen to sequence this talk is to first talk about the Earth and what it looks like from space and what we can learn about the Earth from space, and then to shift over to give you some idea of kind of the sequence of a space shuttle flight and the sense of a space shuttle flight. And I've brought lots of multimedia equipment with me. I've got some slides to show you, and I've got a film to narrate at the end. If anybody has any trouble seeing the screen during this, I won't be offended if you want to get up and quietly move to someplace where you can see it. Sit on the floor if you need to. I think some of you over there may have a little trouble seeing the pictures. But that's the plan for the next hour or so. I'd also, because it's very difficult to plan a talk for a group like this and to take my guess at what you want to hear, I'm also going to try and leave some time for questions at the end, because I'd really like to be talking about what you'd like to be hearing about. So if I don't touch on something that you were interested in, I hope to give you an opportunity to ask me about it at the end. The U.S. space program has actually discovered over the last 20 or 30 years that one of the most important things that we can study from space is not other planets, not the space environment, not the effect of weightlessness on people, not the other planets in our solar system, but is our own planet. In other words, we can look back at Earth from the vantage point of space and significantly improve our knowledge of the planet. And a lot of the things that we have learned about Earth over the last couple of decades have actually been as a result of the space program. Now, what I'd like to do to try and give you a sense of what you can learn about the Earth from space and sort of the range of problems that are addressed by instruments in orbit around the Earth, I'd like to not describe these instruments in very much detail at all. In fact, probably not in any detail. I'm not going to show you scientific data. I'm not really going to be giving you the scientific description of the problems, although I can at the end if you'd like to hear more of that. But what I've chosen to do is to illustrate the features and the phenomena that you can see on the Earth from space by bringing a set of slides of pictures taken by astronauts in the space shuttle looking back down at Earth. And it's actually quite remarkable how much you can learn from those pictures and what a good sense those pictures give you of the value of putting instruments up in space. It gives you a great idea of what the view is from Earth and why it's a good idea to try and study the Earth from above. So I'm not pretending that these pictures that you're going to be seeing are scientific. They're not on the cutting edge. They're not brand new data. They're just good pictures, but those good pictures do a great job of illustrating what the science can achieve if the appropriate instrument is put up in orbit. So again, you're going to be seeing pictures taken by astronauts from the space shuttle to illustrate these points. If we go ahead and get the lights down, and I'll go ahead and start the slides. Excellent, thanks. Okay, the first lesson is this is not what the Earth looks like from the space shuttle. This is what the Earth looks like from the moon. This was one of the pictures taken by the Apollo astronauts who landed on the moon over 25 years ago now. And the view that they had looking back at Earth from 250,000 miles away. One astronaut who had this view was quoted as referring to Earth as a grand oasis in the great vastness of space. That's extremely rare eloquence for an astronaut, and you're not going to be hearing any more of that the rest of today. But the point to make here is, first of all, this is not the view. Everyone, almost everyone, imagines that this is the view of Earth that astronauts have. And shuttle astronauts, space shuttle astronauts, do not have this view. We're much, much, much closer to Earth. And what that means is that we can see a lot of the detail and a lot of the features of the Earth and study the finer scale instead of just getting a glorious view of the whole planet. I've also put this in here to make the point that the space program has really had a huge impact on the way that we view the planet, scientifically as well as philosophically. When these pictures were brought back from the moon by the astronauts, it was kind of our first concept of spaceship Earth, if you like, that we're all on one planet, and the maintenance of that planet is an important part of our future. Now, during the 25 years since the moon landings, scientists have learned an awful lot about Earth. They've come to appreciate that Earth is really a very complex system. It's composed of a whole set of linked, interacting components. So whereas scientists used to study atmospheric physics, or atmospheric chemistry, or oceanography, or geology separately, we now understand that you can't study those disciplines separately. Everything is connected to everything else, including the biosphere and including civilization's impact on the planet. And this has evolved the whole concept of Earth system science, where we study the planet as a whole and we study all these components as interacting components. Now that gives you some appreciation for why it's important to be viewing the Earth from space. In order to get this global perspective, to see the large scale on the planet, you really need to be above the planet in Earth orbit, going around it to be able to get the full view of the planet. So now let's go on to the view that the shuttle astronauts have. And before we get to the view itself, let me make sure that we're all talking about the same thing when we talk about the space shuttle program. So if you'll indulge me, let me go on for 5 minutes about what the space shuttle, a little bit about the space shuttle and what it's done and what orbit it's in. Okay, this is what the shuttle looks like just a couple of seconds after launch. The space shuttle launched for the first time way back in 1981. There have been over 65 space shuttle flights in the 13 or 14 years that it's been flying. So this has now become a fairly common event. About once a month or so, you'll probably see a space shuttle launch on the evening news. Now, the first 4 space shuttle flights back in 1981 were purely to test that the concept of the space shuttle was a good concept. Those of you who've studied the space program or rockets at all know that the space shuttle is completely different from anything that went before it. Rockets used to be nice, sleek, cylindrical things with capsules on the top, and they kind of sliced up through the atmosphere. And the shuttle was completely different than that. It was take an airplane, much like you'd go from Chicago to St. Louis in, stand it on its tail, slap it up against a big, ugly orange tank, and strap 2 things that look like rockets on the side of it, and then see whether you can get that off the launch pad into orbit. And once it's into orbit, the only thing that makes it to orbit is the airplane. All the rest is purely fuel. Everything in the orange tank and the white cylinders on the side is just the fuel that's needed to get the space shuttle airplane into orbit. Once it's into orbit, it's supposed to orbit the Earth like a spaceship. And then, most important to the astronauts, once it's time to re-enter, this thing that looks like an airplane is supposed to act like an airplane and re-enter the atmosphere at Mach 25, 25 times the speed of sound, halfway around the world from where it's going to land with no engines at all, So it's a glider all the way, halfway around the world, slowing down from Mach 25 to landing speed purely because of air friction. It's only air friction that slows down the shuttle during re-entry. And then it's supposed to land on something that's sort of a normal runway at speeds that are sort of normal airplane landing speeds. So the first 4 flights were just to test that this idea was going to work, to just make sure the system worked. And those first 4 flights, each one just carried 2 astronauts. They didn't carry any experiments. And there was a good reason for only carrying 2 astronauts. Because this was such a novel concept, and they weren't sure it was going to work, especially on landing, they wanted the astronauts to have ejection seats. And the ejection seats are huge. You can only fit 2 ejection seats into the space shuttle. And they thought that it would be very, very bad for morale to have a crew of 4 and only 2 ejection seats. So the early flights just carried 2 astronauts. But then after those first 4 test flights, the shuttle the crew expanded to a normal crew of 5, and it started carrying satellites and instruments. This is what the shuttle looks like when it's in orbit, and there are a couple things that I want to point out to you here. First of all, here's your first clue how close to the Earth the space shuttle is. It's only about 150 miles above the Earth in this picture. The other thing that I wanted to kind of bring home to you is how much of the space shuttle is devoted to experiments and cargo, and how little is devoted to the crew. The whole part that's open, that would be like a passenger section of an airplane, is open to space. The crew can't go back there, except on spacewalks. The crew just lives in what's sort of the nose of the space shuttle there. And I can give you an idea of how much room there is. This is the crew from my first flight. And we are stretched from one side of the cabin to the other. Norm's shoulder is against one wall, John's elbow is against the other wall, and we're as far from the camera as we can get. So this is how much room, and then there's one other floor that's got just about this much room in it, and that's all the room there is in the space shuttle. I should point out, actually, maybe just one person in this, Norm Thagard, the guy on your left, you're going to be reading about in probably this spring. He's over in Moscow right now. He's training to be the first American astronaut to fly aboard the Russian space station. So his name is going to be in the news in a few months. Just to give you an idea of a couple of things the space shuttle has done, this is a communication satellite that we launched probably about 5 seconds after it was popped out of the space shuttle payload bay. This particular one was for the country of Indonesia. The crew cabin that you saw a couple slides ago is pressurized. It's just like this room, maybe a little cooler. But you don't need to wear any special clothes. You don't need to wear a pressure suit. If you're going to go outside the space shuttle, you need to put on a spacesuit. And this is what the shuttle spacesuit looks like. This astronaut is in an old version of kind of a Buck Rogers jetpack that astronauts can fly around in so that they don't need to be connected to the shuttle by wires or ropes. The guy in this picture said that what determined how far from the shuttle he was willing to go was just pure fear. I think good description of it. Okay, this is what the space shuttle carried on board my second flight. And when we get to the film, you'll see a little bit more of these various instruments. But I've put this slide in here just sort of as the transition to looking at the Earth. My second flight was purely an Earth-looking flight. All of the experiments that we carried were designed to look back at Earth in one way or another, to study one thing or another. And this is the set of experiments. But what I'm going to do now is go on to the pictures that the astronauts have taken of various parts of the Earth. The shuttle is in an orbit that is roughly 150 miles above the Earth. When you're 150 miles above the Earth and you look down at the Earth towards the horizon, this is how far you can see. This is the state of Florida. So you can see, a couple hundred miles in any direction. If you look toward the horizon, you can see maybe 400 or 500 miles. notice that you can see a little bit of the curvature of the Earth. You can actually see more of it than you might think in this picture, but you certainly don't see the whole planet. You don't even see the whole United States. In fact, you don't even see the whole east coast of the United States. But you can't, the thin blue line up there at the top is the atmosphere. We're above the atmosphere looking down, so that's all of it that there is. Now, if instead of looking toward the horizon obliquely, you were to look straight down, this is the amount of detail you'd be able to see. This is looking down at Cape Canaveral in Florida, the Kennedy Space Center and Cape Canaveral. And there are a couple of things. First, the things that you should notice here are how much detail you can see. You can see runways, roads, bridges. I'll actually point out the space shuttle runway that the shuttle lands on. So you can really see a lot of detail if you look down from that distance. Okay, so let's go into some of the natural features that you could study if you had the appropriate instrument up with you in orbit. This is a picture of Israel and the Mediterranean. And what you see most strikingly in this picture is a real sharp line right there that goes from the Sea of Galilee down to the Dead Sea. That's a fault line. It's really easy to see earthquake faults or seismic faults from orbit. They stand out very, very strikingly as just straight lines in the landscape. If you were to look obliquely at this same picture, this one's really hard to get oriented in, but there are a couple things I want to show you in this picture. First of all, Israel is right up at the top there. So the bottom of the last picture is just about the top of this one. And you can see the straight line extending down. That's one long fault, and it's the same fault that opened up into the Red Sea. So if you wait, several million years, that fault that we saw in the last picture will also have opened up into a sea. And this gives you a good idea of sort of the scale of these seismic features. Also, there are a couple of other things that you should notice here. First of all, subtle color changes are easy to pick up and they tell you a lot. You can see drainage patterns in the desert. You can see different rock formations and different rock patterns just by the different colors. It's obviously easy to tell the difference between water and land. It's also easy to tell the difference between irrigated land and desert. This whole green area here over on the side of the picture is the Nile River Delta. And it's the Nile River that you're seeing going off down here at the bottom. And you're not seeing the water, you're actually seeing the vegetation that grows in the Nile Delta and along the river as a result of the irrigation. This is the Mississippi River Delta. The Mississippi dumping the sediment into the Gulf of Mexico. And if you were to take a picture of the Mississippi River Delta today, and another one a month from now, and another one a month after that, each one would look different. You can almost follow the deposition of sediment into the Gulf and monitor it almost quantitatively just from these pictures. This almost looks to me like a dynamic picture. I mean, you can really see the stuff being dumped into the water. This is what a hurricane looks like from orbit, and makes it easy to see how much information you can get about large-scale weather patterns. This hurricane was about 200 miles, about 300 kilometers across, and was active in the Indian Ocean during my second flight. And if you take a look, the next picture is going to be looking right down the eye of this hurricane. So you're actually looking to the water and seeing the Indian Ocean in this picture, and you can see the structure of the eye wall very clearly here. Not only can you see vegetation on land, you can also see vegetation in the water, interestingly enough. This is off the coast of southern Africa, and actually I've got this thing in a little bit sideways if you want to orient yourself. Those of you who know geography, Africa should be turned this way, but I didn't do that when I went through the slides. So this is off the coast of Namibia, just north of South Africa. And what I want to point out to you in this picture is that the light green color in the water is actually a result of billions and billions and billions and billions of phytoplankton, single-cell plants in the water. So you can actually, and it's the chlorophyll that you're seeing. So you can actually follow plant life in the water from space, and because phytoplankton, as probably many of you know, are the bottom of the food chain in the ocean, where there are phytoplankton, you expect there to be fish. So you can actually do monitoring of locations of plant life and animal life in the ocean from orbit easily. Okay, it takes a minute to get oriented to this one. This is up in Alaska. The top of the picture is just clouds. The middle band is a snow field. Then you see a set of mountains right along the coast, and then a plain, and the bottom of the picture is the Gulf of Alaska. And actually what you can see in this picture is two glaciers, where the glaciers are moving from the snowfield down through the mountains onto the flat plain at the Gulf. And I'll show you the two glaciers. So the second glacier that I showed you, the one that's spreading out, you can almost see from the concentric circles here, you can get a good picture of the surging back and forth of this glacier as it's moving. So ice is actually a very important indicator for global climate. It's one of the important things that scientists like to study from space. Not only can they monitor, believe it or not, the movement of glaciers, but also they can look at ice levels to understand how the climate is being affected. Okay, I wanted to move on now from some of the natural phenomena that you can see, or natural features, to some of the effects of civilization. And what better place to start than with a city? This is the city of Winnipeg in Canada in the winter. And again, in this one, you should just notice the detail that you can see in the picture. You can see the layout of the city. You can see the river that goes through the city. If you look closely, you can see the airports and the runways in this city. This is a picture of the island of Madagascar. And Madagascar is a huge island off the east coast of Africa. It's an island about the size of Texas. And it's a very mountainous island that 50 years ago or so was covered with forests. And in the last 50 years, the people of Madagascar have been cutting down the forests to clear the land for grazing, to clear the land for agriculture, and to use the wood for fuel, basically for burning in their stoves and fuel to keep warm. But as a result, there are only about 10% of the original forests are left on Madagascar. And it's the site of probably the worst example of erosion on the planet. Because there are no trees, the topsoil is just free every time it rains to flood down the mountains. And that's what you can see happening here. You can see the topsoil being brought down in the brown water coming down from the mountains and meeting the blue water of the Indian Ocean. It's actually a huge problem in Madagascar. This is an example of, also an example of pollution. This is the Rhone River in France dumping into the Mediterranean. So France is down here, Marseille is actually over here. And the white plume that you're seeing in the water is actually pollutants that have been picked up by the Rhone as it travels down France, either runoff from agriculture, runoff from industry, or just traveling through cities, and being dumped into the Mediterranean. So it's very, very easy to see pollutants, certain pollutants, being dumped into the water. This is a two-slide sequence. Let me just get you oriented in this one. The shuttle is flying this way, to the left, going over South America. We're actually over the Andes Mountains right now. So the Pacific Ocean is off to the right. Brazil is off to the left. The space shuttle is traveling 5 miles a second, which is orbital speed in low Earth orbit. And about just a couple minutes later, the astronauts on this flight took a look back toward the west. And this is the view they had. The Andes Mountains in this picture are right up there at the top where what look like clouds have stopped. So they're looking all the way across Brazil. This is probably a couple hundred miles across and maybe 500 miles in length. And this isn't clouds. This is all smoke and haze from the fires that are set to clear the Amazon forest during the dry season. This is what Brazil looks like during the dry season. And each of these clouds is a cloud over an individual fire. Here are more fires. This slide has become topical again. This is a picture taken right after the Gulf War. This is Kuwait is over to the left. This is the Persian Gulf up to the top, and Iraq is over to the left. And this was taken after the war, but before the fires in the oil wells were put out. And so the black smoke that you're seeing is the smoke from the individual oil wells spreading, in many cases, 100 miles or more from the site of the oil fire. This is also in the Persian Gulf, but it was taken long before the Persian Gulf War. The Persian Gulf always looks like this. The bright patches that you're seeing are oil slicks, and each one is 10, 20 kilometers across. To get some scale, that's the brown spot in the bottom is a small island in the Persian Gulf. The Persian Gulf, like I said, it always looks like this, and it's very easy to see oil on water for just the same reasons that it's easy to see oil on water, here on Earth in a river. Okay, I put this one in just because I like it. This is what a sunset looks like from orbit, looking down at the atmosphere. And I said the shuttle goes around, is going 5 miles a second. If you do the math, that means you go once around the world in 90 minutes. And if you think about it for a second, that means for 45 minutes you're in daylight, roughly, and 45 minutes you're in darkness. That means that you see a sunrise and a sunset every time around the Earth, every 90 minutes. So we see 16 sunrises and 16 sunsets every 24 hours. So this is just a normal sight on a space shuttle flight. But I put this in actually to make a point about Earth observations. All the other features that we've been talking about and all the other photographs have been looking almost straight down at the Earth. And if you want to study the land or the ocean, that's what you do. Your instrument points straight down. But if your instrument is to study the atmosphere, then what you do is point it off towards the horizon, just the same way this astronaut who took this picture was looking. And this picture shows you why. You can actually see a lot of the vertical structure in the atmosphere. You're seeing thunderclouds going up to about 40,000 feet, up to about the tropopause. You can see the separation between the troposphere and the stratosphere, and a scientific instrument could do the same. So if you want to measure the ozone as a function of altitude in the atmosphere, the way to do it is not to point your instrument down, but to point it in this sort of direction at towards the horizon. Okay, well, this is a concluding slide for this section of the talk, if ever I've seen one. The point of this part of the talk really is just that, over the last 20 years, 25 years, we've been developing the capability to explore other worlds. We've actually acquired an enormous capability to explore our own world as well. And what we've been learning through that process has made a significant impact on our total knowledge of Earth, and that process is just starting. The more we learn, the more we realize we don't know. So this is really a subject for the future. It's a major part of NASA's program for the next, I'd say, at least 20 years or so. Now, what I'd like to do is completely change gears on you. That's enough of the slides. And I'm going to try and give you some idea of what a shuttle flight is like. And before I start the film, let me give you just a little bit of background on it. As you've seen from these slides, astronauts are just like tourists. I mean, we go out to the launch pad with a camera in every pocket, and when we get on orbit, we take pictures of each other, and we take pictures of our experiments, we take pictures of the Earth, and literally the first thing a crew does when they land is go to the photo lab and look at all the pictures. And we select a few, we select some film, and the people in the photo lab put together a film clip that we think best represents the experience that we've just been through. So what you're going to be seeing are the home movies of what NASA called STS-41G, which was the 13th flight of the space shuttle. It was a flight of Challenger. It was an Earth-observing mission. There were 7 of us on board the crew. That was the largest crew to fly to date. A normal astronaut crew, as I said, is 5 people, usually 2 with test pilot backgrounds and 3 with science or engineering backgrounds, and those are the career astronauts that fly. We also had 2 visitors on our flight. One was the first Canadian astronaut, and the other was an oceanographer from the Navy who was there to look at features in the ocean. I guess we were in orbit for 9 days. We landed on the 10th day. You're going to see me using the robot arm to reach into the shuttle payload bay and release a satellite into orbit. That satellite's called the Earth Radiation Budget Satellite, and it was monitoring, among other things, the greenhouse effect for several years. We also carried a big radar that you'll be seeing and a couple of other Earth instruments. We had a spacewalk on our flight. Kathy Sullivan and Dave Liestma got to put on the spacesuits and go outside the space shuttle. And what they were doing was testing an idea to see whether it was reasonable for astronauts to go out and refuel satellites that are up there. For astronauts to actually go out to a satellite that's run out of gas and carry gas cans over to the satellite and fill it up to see if they can extend its lifetime. So when you see the spacewalk, that's what Kathy and Dave will be doing. We landed in Florida at the Kennedy Space Center, so you're going to see a Florida landing. And I think that's probably enough of an introduction. Why don't you go ahead and start it. This was our crew patch. Every crew designs their own patch. That's the astronaut symbol in the middle that's shooting up into the American flag. This was about 4 hours before launch at the breakfast table. We're trying to look nonchalant, like nothing unusual is about to happen to us. That's Kathy Sullivan, Paul Scully-Power, the oceanographer. There were 7 of us on this crew, and I think that just about maxed out their breakfast table in the crew quarters. We launched a little bit after 7 in the morning, not at night like it looks like here. But because the shuttle main engines and the solid rockets give off so much light, the cameras had to be stopped way down just to avoid being overwhelmed, so it looks like we're launching at night. Now, the first thing that happens is that the shuttle engines light, fueled through that big external tank. And once the computer is satisfied that the engines are working, then the solid rockets light, and then you're on your way. There's nothing that you can do to stop things at that point. The solid rockets provide most of the thrust. They only burn for 2 minutes, so their fuel is all gone in 2 minutes. At the end of those 2 minutes, you're already 25 miles away from the launch pad. And the solid rockets are pushed away, and they fall back to Earth, and you'll be able to see that in a second. After the solid rockets are pushed away, then the shuttle keeps going into orbit just on the strength of the space shuttle main engines getting fuel from the big tank. And here the solid rockets are about to separate. They're the 2 pencil-shaped things that you'll be able to see coming off to the side. It takes about another 6.5 minutes to get to orbit, so it's a total of 8.5 minutes from ignition on the launch pad till you're weightless in orbit. This was just a couple of hours after launch. I've already taken the robot arm and used it to hook onto the satellite. You can see the arm coming in from the upper right of the picture. We control it from inside the space shuttle. And the idea here was to use the arm to lift the satellite slowly up out of the shuttle's cargo bay and get it up over our overhead windows so that we could do a thorough checkout of the satellite and make sure that it was working before we released it into orbit. Again, this is a satellite that was called the Earth Radiation Budget Satellite. And here I just released it, and now I'm pulling the robot arm very slowly away from the satellite. So at this point, the satellite is in orbit all by itself. It's not attached to the space shuttle at all. And that means that the space shuttle and the satellite are both traveling 5 miles a second around the Earth. And these shots give you an idea of how stable the space shuttle is. I mean, it really looks like you'd think these things are just standing still, but they're actually moving 5 miles a second. John is firing the space shuttle's very small little jets to move the shuttle away from the satellite and leave it behind in orbit. It was in orbit for about 7 years, gathering information on the Earth. This is Kathy at one of the shuttle's computers. She's a geologist, so she had a lot of interest in some of the experiments that we carried on the flight. This is the big space shuttle radar that when we launched it was folded up. We had to unfold it, and you'll see it in just a second. That you'll see that it took up most of the space shuttle's cargo bay once it was unfolded. And it was a radar experiment that was looking at seismic faults, looking at features in the ocean, including ocean currents and volcanoes, volcanic activity. That was a large format camera that we carried. And this was an experiment to look at the carbon monoxide content of the atmosphere. Now you get to see a few more of our tourist pictures. This is coming over Gibraltar. And here's Paul Scully Power. This was early in the flight, so he didn't know where the cameras were yet. His job on the flight was to look out the window and see if there were features in the ocean that he could see, that he could detect, that the instruments did not pick up. And there were actually several features that he saw that the experiments didn't pick up because they weren't intended specifically for that. This is the island of Crete. And here's Dave looking out over the Red Sea, I think. Yeah. This picture gives you a sense of the motion of the space shuttle. This is what 5 miles a second looks like against the background of the Earth. And here's Mark, the Canadian astronaut, with a solar physics experiment. Now, through all of this, you should notice that weightlessness is definitely different than being in this room. Kathy's hanging from the ceiling. The books don't always stay where you thought you put them. Pencils don't stay where you thought you put them. And in fact, you don't stay where you thought you put yourself. The space shuttle has a whole set of foot loops so that you can slide your foot in to stay in place. You'll be able to see one in a minute. John's got his foot in one down here at the bottom of the screen. So that's how you anchor in place instead of floating in the middle of the room. Now, about halfway through the flight, we ran into a problem. Before Kathy and Dave could go out on their spacewalk, we had to fold the big antenna to give them room to move around. And we could fold it, but we couldn't get it to come down quite all the way, so we couldn't get it to latch in place. So Mission Control asked me to use the robot arm to try and push down on the antenna to see if we could push it down far enough for the latches to come over it and hook up. And that turned out to be actually pretty easy. So Kathy and Dave started pulling out their spacesuits for the spacewalk. Again, the atmosphere in the crew cabin is just like it is in a room on Earth. It's the same gas composition. It's temperature controlled. The carbon dioxide is removed from the atmosphere. So you just wear regular clothes as long as you're inside the space shuttle. But if you're going to go outside into the vacuum of space, then you have to put on a lot of protective gear. This is actually the liquid cooling garment that goes on underneath the spacesuit. It's got thousands of little rubber tubes that carry water, and the water runs along your body and removes the heat. So that's how your body temperature is controlled. The spacesuits actually contain everything that an astronaut needs to live for several hours. They're pressurized, they've got the air to breathe, they've got water, radio communications with us inside the shuttle and with Mission Control down on the ground. We didn't carry the backpacks, the jet packs on our flight, so you'll see wires attached to Kathy and Dave's wrists. There's always one end of the wire attached to the wrist and one end of the wire attached to some part of the space shuttle. And here's Dave working on the gas refueling experiment. We carried 2 gas tanks up with us in orbit. They're both behind this bulkhead. One of them was full with rocket fuel, basically, and the other was empty. And the idea was to see whether in weightlessness and in the big pressure suit Dave could make the connection between the tanks, and then if that connection could be made, then whether in weightlessness you could transfer a liquid from one container to another. So here's Dave making the last connection between the two tanks. That turned out to be fairly straightforward. Dave was able to connect the tanks pretty quickly, and the fuel transfer worked pretty well. So that's something that is a reasonable thing to think about in the future. There were a couple of other things that went wrong on the flight that Mission Control asked Kathy and Dave to take a look at, sort of as long as they were out. One of them was the Space Shuttle communications antenna. It's the black antenna that you see here. It had failed early in the flight. We couldn't move it. So they had Kathy and Dave go out and kick it, I think, to try and get it to move. And you can see that it's working now. They also wanted Kathy to take a look at the radar antenna and see if she could tell why we hadn't been able to get it to fold up completely. And it turned out there was just a little puff of insulation that was in the way. But because in weightlessness, motors don't need to be strong at all, these motors were made so light that they couldn't even push down a little puff of insulation. The spacesuits can keep an astronaut alive for 7 or 8 hours. Kathy and Dave were out for just a little bit over 3 hours. Now again, this will give you just a little bit of an idea of what it's like to try and live and work in weightlessness. We carried a set of experiments inside the crew cabin as well. This was an experiment to monitor the radiation level inside the space shuttle. Now, we spent the whole week trying to figure out what Paul was doing in this experiment. We still have no idea. This is Dave on the treadmill. That's the only piece of exercise equipment that we carried up for the roughly week-long space shuttle flight. And here's John starting to make lunch. Those are food trays that he's velcroing to the wall. Everybody's got a food tray, so the person that's in charge of making the meal pulls out the food trays, velcros them so that they stay in place, and then puts the food into the individual food trays, and we pass them around. Now, Mark is going to demonstrate his technique for eating carrots in weightlessness. Now, this is what it looks like at dinner time in the space shuttle. You can see that there really isn't much of a need to have a dining room table or dining room chairs. And in fact, this gave new meaning to the phrase, "pass the bread." Okay, now here's your pop quiz for the afternoon to see if you can remember how many crew members there were on board this flight. We're coming down from what's called the flight deck. It's where the controls for the space shuttle and the robot arm and a lot of the experiments are. Onto the mid-deck, which is kind of the living area where we store the food and usually eat our meals. And those are the only two rooms in the space shuttle. As somebody said, this is your tax dollars at work. This is sort of a bad picture of Hurricane Josephine. It was a hurricane that was active off the east coast of the U.S. when we launched. There was concern that it was going to come over Florida and that we were going to have to land in California. But it turned out that the weather cleared out and it was a beautiful day in Florida, so we landed at the Kennedy Space Center. This is the shuttle coming in. Now it's just gone below Mach 1. It's subsonic. The computer flies it down to Mach 1, and then the commander takes over. So Bob Crippen is flying the space shuttle at this point, and it's got no engines at all. It's a glider and has been halfway around the world. So the space shuttle is about to land. And take a look at this landing. I didn't even feel this when the wheels touched. As I said, we landed in Florida at the Kennedy Space Center, and the Kennedy Space Center is part of a large wildlife preserve. And after they poured the concrete for the space shuttle runway, they went and dug a moat all the way around the runway and then filled the moat with alligators. So it turns out that there's a huge incentive for the pilot to land right in the middle of the runway. This is just about 30 minutes after touchdown. It's a great way to spend a week. Thank you very much. It looks like we've got time for a couple of questions. So if anybody's got a question, and if there's a chance that I can see you, go ahead and ask. Yeah. Okay. The question was, what happened to the Soviet space shuttle, the Buran? The Soviets, Russians, many of you may know, built a space shuttle that is identical to the space shuttle. It looks exactly the same. In fact, if you had them right next to each other, you wouldn't be able to tell the difference except for the flags on the wings and just one or two other differences. They launched it only once. It's only flown once. They launched it without people. There were no cosmonauts on board, so they launched it, and it landed with an autopilot. And it was a very successful flight, and it's never launched again. And probably the reason is just that the Russian space program is based around a different concept than ours. Theirs is based around, they still launch their cosmonauts on rockets, in capsules on top of rockets, up to a space station. They've got a space station that's in orbit right now called Mir, that's been in orbit for, I guess, 8 years now. So they have a different way of getting their cosmonauts to orbit, and they've got a space station that's up there all the time. So they didn't really have a use for a space shuttle in addition to that stuff. So they announced that they canceled the program just, I think, about 2 years ago. I can't remember when it flew first. I want to say it was like 1988 or something like that. It didn't fly for several years, and then a couple years ago they announced that they'd canceled the program. And I haven't seen this yet, but I've actually had 2 people now tell me that they've moved it out into a park, and it's a restaurant and amusement park in Moscow now. Yeah. When you're upside down, does the blood go to your head? No. And the reason the blood doesn't go to your head is that everything in the space shuttle and everything in your body is weightless. So you're weightless, and what that means is that on Earth, when I'm standing here, blood is being pulled down to my feet. Okay? When I'm weightless in orbit, blood isn't being pulled to my feet. It's not being pulled anywhere. It's just free to kind of float around in my body. And the result of that actually is that the equilibrium position of fluids in your body is different in orbit than it is on the ground. And that means that there's more fluid, generally speaking, in the upper part of your body than there usually is on Earth. But it's not because the blood's being pulled to your head in weightlessness, it's because it's not being pulled to your feet. In fact, if you look at pictures of astronauts in orbit, they all look like they've got kind of puffy faces, puffy cheeks, and that's the reason. There's much more fluid in your face, even when you're upright in the space shuttle, whatever upright means in weightlessness. But if you can't tell the difference, you can't feel any difference physiologically in the space shuttle, whether you're oriented like this, or like this, or like this. You don't feel any difference at all. Yeah. Could you say it again? Okay, the question was, do I think that we'll have industry in space, and if so, what kinds of industry? I think the jury's still out on that. There are a couple of industries that have been built around objects in space that are very successful, and only a couple. And one of them is communication satellites. The communication satellite industry is a huge industry and a very successful industry that's just taken off. But if you ask about other industries, like there was talk for a long time of being able to develop pharmaceuticals in space, because on Earth, liquids, for example, that you get sedimentation. In orbit, you don't get sedimentation. The gravity doesn't pull one down over the other, so fluids mix. Other objects tend to mix and not settle out, and that gives you lots of opportunities for manufacturing things. Most of that to date has been basic research on the feasibility of things. It's not clear yet whether any of those are actually going to take off into industries. The pharmaceutical probably would have, except that it's sort of been overtaken by biotech. So there are still certain areas that make sense and that you could only do in space, but it's not the huge array of them that people thought it was going to be back in the mid-1980s. So it's really hard to say. It's probably the next 10 years or so that we're going to find out the answer. So, okay. The current state of freedom? Yeah, the question was, what's the current state of space station freedom? Let's see. It's a little bit of a battle every year in Congress. It made it through Congress again this year, but it's been changed significantly in the past year, and the changes are really fundamental. First of all, it used to be an international space station that where the partners were the United States, Europe, and Japan, and Canada. And significantly, in the last year, Russia was added as a partner, and not just added as, you know, you guys get to add a module. It was, the space station was fundamentally redesigned to include Russian as well as American components, using Russian pieces as well as American pieces, Russian systems as well as American systems, and Russia and the United States are really the two senior partners in this right now. So it's been actually a huge change, and they've made it more of a phased program, so that the first phase is actually going to be, and this is going to happen next spring, just like in 6 months. The US space shuttle is going to go dock with the Russian space station, Mir. And right now it's scheduled to do that 7 times over the next 3 years or something like that. So the idea is we and the Russians are going to learn how to work together and to build a space station by first sending the shuttle to their space station. And then we're all going to work on building a much bigger and much more capable space station that right now it's being called, it's actually not called Freedom anymore. They just changed its name a little while ago to the International Space Station. So presumably, since that's not a great name, its name is undoubtedly going to change again. But that's the state of it. And I can't remember, I think they're supposed to start building it in 1997 or 1998. How about one more question? Yeah. You. What? Okay, then we'll take 2 questions then, because that's one of the winners. The question was, do you take showers? And the answer is no. It's a short answer. There's no shower on the space shuttle. So of course what they've got is washcloths. So it's as if you were on a camping trip for a week. So you've got washcloth and a hose. Okay, let's see. One more question. One more time. How do uncontained liquids behave in space? That's actually a great question to end on. If you take a glass of orange juice or a carton of orange juice and you just open it up and get the liquid out, and there's no such thing as pouring, remember, so you've actually got to kind of just push the liquid out. If you do that, you'll get a ball of orange juice. It'll turn into a spherical ball and it'll just float in the middle of the cabin. And it is a neat physics experiment because you've got this sphere of orange juice that you can poke and it'll start oscillating with the normal modes of a liquid sphere, and you could actually stick a straw into it and drink it. Thank you very much.
On behalf of all the students at the Academy, I'd like to present Dr. Ride with this little souvenir of our school.
Sally, when you come back, I hope that we see pictures of you in space wearing your IMSA sweatshirt. On behalf of all of us, we want to once again thank Dr. Ride for this extraordinary presentation. The Academy calls itself a pioneering educational community, and I think Dr. Ride has showed us what pioneering is all about. We want to thank you, our visitors and guests, for being with us today. We hope that you see the Academy as your institution, and we welcome you at any time. There are information materials as you leave. Once again, thank you for attending, and those who will be attending the reception will be taken there shortly. Thank you and good afternoon.